All right. Good. So let me hear what your question was.
Like, what is the reason why we got VA times Z1 over Z1 plus Z for VB? Like, for example, I understand why Z1 is equal to R in parallel with R plus Z, right? But like, how they got that equation for VB?
Right. Okay. So we starting at the output and we moving in. Right. So if we start from V out, right? If you look at it, V out, we labeled here as VB and VA. So let's start from the output and go back. This point V out will be VB over R plus whatever is the impedance here, which is Z multiplied by R. So that takes care. We have V out in terms of VB. Now VB itself, right? If you look at VB, first off, looking down this way, notice we have R in parallel with these two things here, right? Right, if you're looking in this direction, what this point seeing is R in parallel with this impedance here, which is this. Fair enough?
Right, yeah.
Right, so that the voltage VB is now VA, which is the voltage here, and you have an impedance divider at this point. Right, that's why you have, so you're getting VB now in terms of VA, like that. And then the last thing now is that you try to get VA now, which is in terms of VIN. And what VA is seeing is R in parallel with all of this now, which is this one. Right? So that this now is another impedance divider. So basically what you have is the capacitor here and an impedance. So this is VA and this is VIN, right? And this Z, that impedance is Z2, this whole thing here. Any clearer?
Isn't that up capacitor is the full Z? The top capacitor, right, is the one that is circled in red.
Yeah.
All right. Yeah. Understand now.
Right. So it was like what I drawn before. If you think about it in terms of resistor networks. Something like that, right? Here, and we're taking our voltage coming out here. So here is a normal resistor, a potential divider, right? If you look at this second leg here, at this point, we have this leg in parallel with this leg. And once you calculate that now, then you have another potential divider here. And then here, seeing this in parallel with this, in parallel with this. We already calculated this from before, so it's just basically this in parallel with that, and that gives you another one. And then you have the answer here. So you kind of work backwards from the output to the in. The simplifying is long, right? I was trying to see if it would make sense to put it up for you all, right? And I have it there. I'll put it up. I'll finish. I'll just want to write it over neat because it is very, very long. And I think that's why we just kind of put the answer up inside of here, right? Because once you start to eliminate now, because this is what you have you have to substitute for and in fact, instead of doing this, I think it's easier if you put SC1 over SC for this and R, and then you just keep going, and then you make the substitution S equal J omega, and then you will get down to this bit here. All right. But I'll put it up because it's really more algebra than anything else. So I'm kind of more interested in the principle behind it, that people understand what how the divider network work then. But is that any clearer now?
So why would it be Z1 over Z1 plus Z? Because
let's get rid of some of the mess here. Right. So good. So Z1 Z1 is these two things together now. All right, that's what we have here. This is Z1 here. So if you want to redraw the circuit, basically what you have is this. This is VA here, right? And we're coming down here to a capacitor and then an impedance, right? This is the capacitor here, and this impedance here is Z1, right? And Z, of course, is this, right? So VB, which is here, there's a potential divider, so is VA over Z plus Z1 multiplied by Z1. Yeah.
so that capacitor within Z1 will form that impedance below the capacitor you have through there.
This one?
Yeah.
Yeah. This capacitor is now part of the Z1 here, right?
Right.
So but Z1 related. Z1 is the capacitor impedance is this, or 1 over SC if you want. Right? So Z is 1 over SC. Z1 is R in parallel with R plus Z, which will be just like you had before, R over SC over R plus 1 over SC kind of thing. Right? So that is Z1. And Z2 will be Z1 plus will be R in parallel with Z1 plus Z. Yeah.
So the voltage at B, right? It will be starting from VA.
Right.
So
is this. The voltage at B is this is VB. So the voltage at B is VA over Z plus Z1, right? Multiplied by Z1.
VA times Z. What about the resistor underneath the VA? We considering that as well?
No. We considering that when we start to find VA in terms of VM, right? At this point, we know on this branch here, we're trying to find VB in terms of VA. You remember step one is to find V out in terms of VB. Step 2 is to find VB in terms of VA. And step 3 is to find VA in terms of VN. And once we do that, we eliminate VA and VB, so we get V out in terms of VN. which is what we want, and then we simplify it.
So for
So
now, we just focusing on that capacitor C and Z1
yeah.
that you drew there,
Mm-hmm.
ignoring the resistor below point VA.
Correct. Until you reach to calculate VA in terms of VN, because at that time now, when you're calculating VA in terms of VN, the what do you call it? Let's get rid of this here now. When you're ready to calculate VA in terms of VN, what you now have is Z, which is the capacitor. This is VN, and you now have Z2, right? And this is VA here, right? And Z2 was something that is that resistor R, which is here what he was asking about, in parallel with all of this, right? In parallel with this whole set of resistors and capacitors here, right? That forms Z2, and that is this. So R in parallel with Z1, you know what Z1 is, and Z1 is R and Z, and you know what Z is, right? So you're substituting all the way through. So from here, so you have the relationship that you have here. So this is basically like that. So if you go backwards now, we have V out in terms of V in, once you eliminate A and B.
Yeah, I understand now.
Right? But it's long. It takes a so this is it when you eliminate everybody, but you have to substitute for Z1, which is this, and Z2, which is that. Right? And is in fact this is the phasor approach, and I think the easier approach was actually to use instead of using the minus JXC part, to use the 1 over SC, and at the end make the substitution S equal to J omega, and then simplify it, and then you get it into a long equation that if you know that will have omegas and RCs in them. And then if you make the substitution, if you group the real part and the imaginary part, you'll get it in this form here. Yeah.
Right.
But I'm not going to ask people. I realize that is not something that I could ask somebody to I wouldn't ask you all to do that to derive that in the exam. That's a useful thing to put in the problem set, and I'll probably do that next time. But it's too long to try to. It's a circuit theory question rather than an electronics question, right? And it's just too long. All I'll be doing at this point, we could probably stop. Could probably stop at this point here, on this slide, without simplifying, because to go beyond that is now circuit theory and algebra, which not testing any electronics knowledge anymore. Right? You remember the sort of outcomes for this course is to test electronics, to make use of the other things that we know, but is to evaluate if you understand how the oscillators work, how the lead network work, or how the lag network would work, and what the answers would give you, not so much in the exam to derive the answer. Okay?
All right. What's the reason why eliminating VA and VB?
Yeah, because you want the answer in terms of you want the answer. Remember the transfer function of what you're interested in is that the RC network has to have a transfer function in order to satisfy the Barkhausen criterion, is oscillator. So whatever that network does, you have to have the values of R and C to give it a phase shift. In this case, is a lead or a lag, I can't remember, but it's to give it either plus or minus 120, 180 degree phase shift. And when you hook it up, so you have to, once I calculated what are the values of R and C to give me that 180-degree phase shift. And that is from input to output, right? The VA and VB are just intermediate values to help us to calculate, to simplify and get to the answer. But the transfer function really is V in and V out. Yeah?
Yeah. And it have a power supply question from last year problem sets that are not fully understand. They asked us to design it.
This was December?
It's from last year PowerShell.
Last year's past paper?
Not a past paper, it's from the
December exam?
the problem set solutions. It's the problem set one.
Okay. You want to pull it up? Pull it up for me so I can see what
All right. You see in the problem set?
Yeah.
Right. So they asked us to design a regulated supply using this circuit above with rate at 9 volts at 0.5 amps. They told us that we have to use a 12 volts transformer with 2 volts peak to peak and current gain of 150.
Right.
Where this came from, the 16.97.
12, okay, 12, the 12 volt transformer. 12 by 1 point, well, 12 by root 2 is how much? 16.97, right?
12 by root, right? So
right, so the unregulated DC voltage will be 70, at no load will be about 17 volts.
then the 2 volt.
Right, I think, I corrected that in a later solution, right? So if it's a 2 volt peak to peak, then the peak voltage is 17 volts. And so the 2 volts peak to peak mean it will be actually 17 minus 2. Right, so I think what I'd done is originally when I did the solution, I thought I told people that it was a 1 volt peak ripple, right, instead of a 2 volt peak to peak or something. So it was so I had a little error there, right? So it will be like what we so it will be 17 minus 2 will be the minimum voltage at the unregulated side,
which is 15 volts.
15, correct, yeah. All right.
Then you assume that ICQ is 5 milliamps.
Right.
And IC equal to, why choose IC equal to 10 milliamps?
Right. When we were talking about Zener diodes, and I think it was somewhere in one of the lectures that unless you're given information from a data sheet, most small signal Zener diodes or small power Zener diodes would work well with a bias current of between 5 and about 20 milliamps. So you could choose any value, any reasonable value between 5 and 20 milliamps. That's what I tell you to in the questions you will see things like state any assumptions made. So one of the assumptions will in here you will say, okay, using a Zener a current of 10 milliamps or 5 milliamps or 20 milliamps. Right, but usually it's not more than that. is somewhere between 5 and 20, and you're free to pick what you want. Right? Same thing with the transistors and so on. The typical small signal transistors, the ICQ for them typically is about 5 to 20 milliamps. Right? So kind of leave that up to choice unless I specifically want, if I'm more interested in how people go through the design rather than the actual answer, I will leave it like this. But if there was something specific that I wanted people to do, I will tell you to use ICQ or to use IZ equal to some value that I will give. But if it's not given, you state that and you tell me that I'm assuming that ICQ, for instance, is so and so, and IZ is so and so, and VZ too. You'll have to. Did I say what value Zener to use? No, I didn't.
No.
Right. So you could choose a Zener diode of your your desire, whatever value you want, within reasonable thing. If it's a 9-volt supply, you can't choose a 9-volt Zener. Right? Okay, and if you look at the transistor there, because of the VBE drop, right? You have to make sure that you remember that the Zener, there's a VBE drop on is TR2, that is the lower transistor, right? So there's a VBE. So whatever the Zener diode is, the base of that transistor has to be 0.7 volts more than that, right? And so you have to make sure there's a diode. You try to get it as close to half VCC as possible. That is typically a good design, right? And not too big, not too small. So half VCC here, a good size would have been. You gotta choose a 4 volts and you could choose a 5 volts. Yeah, all right. You would not choose a 8 or a 9 volts because then you'll run into problems, of course.
The voltage across for TR2, the voltage should be 9.7, 9 plus the 0.7 to give it the 9.7.
Yeah, you're reading from something or just looking
at it? No,
huh?
I'm just watching R3, right?
So, 3?
Yeah.
Right, okay.
So, since V out is 9 volts, right?
Good.
And it will be the 9 volts plus the 0.7. That's how they got that 9.7 volts. So
right.
Then they take the 16. Is that already 16 or 17?
Yeah, I as I told you, I had used a 1 volt instead of the 2 volts. It should be 15 there, right? Because 15. We said that, yeah, at full volts, at full current, the at maximum load, then the voltage at the other end of R3 would be 15 volts, right?
So it could be 15 minus 9.7 all right. Over the 5 milliamps.
Which is what the diode requires.
With this 3 point, this is TR1.
Yes, right? Correct.
Okay, so we got that.
Yeah.
So IB is equal to 5 milliamps over 150 for the gain, which is 33 microamps.
Yeah.
Current through R1 plus R2 will be 10 by 2.
About 10 times that. You remember from your normal H bias in your transistor and so.
Yeah.
Right, and that's how I get the 2 values of the resistors.
Is this on this?
Yeah.
This has to do with current biasing.
Yeah, that's the voltage divider or the H biasing to turn TR2 down on, sorry, and that is it. The base current typically in the voltage chain, you want that carrying about 10 times the current through the 10 times the current that the base of the TR2 will require. Right? If it's carrying that much, it means that TR2 will only take 10% of the current through that. So it does not affect the voltage drop. If TR2 is taking about the same current as in that potential divider chain with R1 and R2, then what will happen is that as TR2 turns on or off, depending on how the regulator working, you're going to get the potential divider is going to change, is going to pull so much current through the potential divider because it's taking the same amount of current as a potential divider. It's going to change the how the potential divider works. Right, and at that point it wouldn't regulate properly. So what you're saying there basically is that you want the current. If you think about it, if you think of R1 and R2, the R2 is in parallel with whatever is the impedance of our transistor. Yeah.
Yeah.
Right. So if the impedance, what you want is the impedance of the transistor to be very big compared to R2. Otherwise, when you connect it like that, you're going to, you remember once you connect a resistor with a value that is smaller than the overall value is going to drop. Right? So you're by limiting how much current going through the transistor, you're making the, as far as R2 is concerned, you're sort of making the resistance of the transistor very big. So when you put it in parallel, it doesn't change the value of R2 that much. Right? That is all things that you all would have learned, like with H biasing and that kind of thing.
For R2, right?
Yeah.
That, how they got the 5 volts? It could be 5 plus 0.7, but that 5 volts.
For R2?
Yeah. Watching here.
Right. The diode is 5 volts. I think I choose a 5 volt diode. So that if the emitter of TR2 is at 5, the base is going to be at 5.7. Of TR2, huh?
You see?
That makes sense. Good day, everyone.
Hi, very good.
Surviving. I run away from work from everybody.
Yeah. Yeah, we just have another talk here. It's being recorded, so you will see what we're discussing as well.
But that makes sense, right? Because the Zener need to be half the output voltage, and the output voltage is 9. So you do a 5, that'll be 5, and the base will be 5 plus 0.7.
Correct. You see that, Kamraj?
So the voltage at the emitter does normally be equal to the voltage at the base. Said that wrong.
No. For TR2 to turn on, the base has to be 0.7 volts higher than the emitter. And we have fixed the emitter at 5 volts because of the Zener diode D. All right, so if we fix the emitter at 5 volts, the base has to be 0.7 volts higher than that, which is the 5.7.
So let's say if it didn't have a Zener diode over there, what would be the voltage at the base and the emitter?
No, well, if you didn't have the Zener diode there, what you have to have something there. If you just had a short circuit, then the emitter would have been 0 because it would have been grounded, and the base would have just been 0.7 volts.
Oh, right, that makes sense.
Right? So
R1 will be 9 minus the
5.7, right? Yeah.
So C is equal to 0.5 all over 2 by 60.
Yeah. Yeah, assuming it's at 60 hertz. Of course, if you're somewhere else, I think like Barbados, I believe is 50. I know Guyana is 50, I think. So it's under their conditions, the value of the capacitor will be a little bit different. All right.
the question does not state the frequency to be using 60 hertz, right?
Yeah,
Yeah.
use 60.
You're in Trinidad? Unless
Yeah,
you live on a boat.
all the way in Trinidad. So cameras to specify, you know, I is the current that the power supply. Suppose you wanted the output. The 2 is because full wave rectification, delta V is the ripple, and F frequency.
Yeah.
If it was half, we'll just use delta V. This is as far as I reach in power supply. I reach up to the op amp, and then after I need to do that.
The op amp actually is a fairly easy design because you don't have the base transistor to consider in that particular design itself. You just really have to get the voltage divider, the sensing resistors then, and the bias resistor for the Zener, and then everything else is the rest is there. You don't have too much more to do. It's a very nice, straightforward design. All right, and fairly simple to work out in exams and that kind of thing. This kind is a little more complex, and then of course if you put in the third resistor with the overcurrent, whether it's fallback or just straight current limiting, then you have a little more calculation work to do.
I would say if you brought this in exam, I would be more comfortable because I know I don't really understand the operation of the op amp at this point in time.
Yeah.
I mean, if I know it's like almost 10, but if you have time, that would be nice if you could go through it.
Well, actually, we were talking about that this morning here. That one is quick. Kamaj, if you want to stop sharing, I'll put back up the op amp thing for you. Right, so let me see if I still have that. Yeah. Okay, okay.
Anyway, Kamraj, if you want to know like fundamentally how the other one does work, I could probably explain that for you.
Right, so here's a very, right, we were talking about all of this. Let me see if I can just let me close off this without saving. Right, so yes. Okay, let me try and find that one again. That was the revision problems that we were looking at, right?
Yeah, I believe it has a op amp in that one.
Right, yeah,
in general.
That's what we were talking about, right? So the revision problems. There we go. Right. Yeah, this one. There's the one we were talking about. Right. This one basically, instead of the difference with this here is that instead of driving the base of the transistor with another transistor to work, we let the op amp do that for us. And all this op amp is doing is working as a comparator. It's comparing the standard voltage, which we set by the diode, to a sensing voltage that we have here. Right? Let me just get something else. There's a touch screen here, so I have to use a different technique. All right, let me see if I can get this looking here. Right, so what we do, just like we have with the the transistor, we need a reference voltage. So we set the reference voltage using the Zener.
Right.
And because of the virtual earth behavior of the op-amp, you know, it's right now it's just working as a comparator. It's an open loop amp. Doesn't have any feedback resistors in it. It forces this point, because of the virtual earth, here has to be VZ as well.
Mm-hmm.
Right? So once here is VZ, regardless of what the op-amp is trying to do now is to maintain here. This is clamped because of the Zener. The op-amp is by the virtual, whatever it does, it wants to maintain VZ at that point. So if this voltage goes up, for instance, for some strange reason, the potential divider between R1 and R2 is going to try to make the voltage at this point go up. But the op-amp has to keep that at VZ. So what it's going to do is it's going to remove current from here. Remember, it's supplying current to the transistor to turn it on. What it's going to do is to start reducing the amount of current so that this turns off. In other words, it conducts less, so the voltage starts to drop back again until it reaches VZ, and then it stabilizes. If for some reason the voltage goes down, then the op-amp has to try to keep here at VZ. So it's going to drive more current to the transistor to turn it on more, force it to conduct more, and send that voltage back up. Right? And that's that's all the op-amp is doing. Right? The previous circuit had the little transistor here. So what had happened is that you clamp here by the Zener voltage, and here would fluctuate up and down depending on what the power supply was doing. And if it went up, then remember this has to maintain a 0.7 volts to keep the transistor on. If it turns on higher, you're trying to increase the voltage here, is going to pull more current through the transistor to try to bring it back down again and get that back down to 0.7 volts. So it's the same sort of principle. Right? But all the op-amp is doing is trying to maintain the voltage at these two input terminals to be the Zener diode voltage.
Stupid question, right? Does this modulate the output current by increasing and decreasing voltage?
Does it
To the
modulate?
transistor?
No, it's the other way around. What happens? This is a constant voltage power supply that is designed to drive, like in this particular one, is designed to supply up to a particular amount of current. So 0 to 2 amps is what this supply is supposed to design, but at a constant voltage, right? What happens is that as you vary the current that you're asking the transistor to supply, the transistor has to keep this voltage at 15 volts up to 2 amps. So at 0 volts, you're supposed to have at 0 amps, sorry, you're supposed to have 15 volts coming out here. At 2 amps, you're supposed to still have 15 volts coming, right? And that is, so it is a voltage regulator, and it is being controlled. What is controlling this is the op-amp supplying current, base current, to turn on or turn off the transistor. That is all it's doing.
Yeah, so like my question specifically was, in terms of the op-amp supplying current to the base, if the output, okay, if it does increase the output voltage to decrease the current, or decrease the output voltage of the op-amp to increase the current.
No, it's just is increasing the current. The voltage has to remain the same, because if he has 15, this output voltage will remain at 15.7 all the time. Internally to the op-amp, what it's going to do is that if the transistor, if you have no current here, the current coming out of the op-amp is going to be nothing, right? As you start to take current here, to turn on the transistor, right? The base current of this, and you don't use it in the calculation, but if you look here, you see the transistor has a current gain of 100. So at 2 amps, you need 2 over 100 amps coming into the transistor to turn it on. So the op amp will supply 2 over 100.02 amps just to make the transistor, right? 200 milliamps to make the transistor operate, right? At full load. So all it's doing is varying the amount of current drive that is providing to the transistor, but keeping the voltage at the output of the op amp constant at 15.7 for this particular one design.
I grasp the concept of operation. Now I just will need to learn how to do calculate the resistors for this.
Well,
is it the same as the transistor?
The resistance is actually easy, very easy to calculate this one, because all you know this. The thing is that once you choose the value of the Zener diode, it means that you have chosen this point here. So if this is whatever voltage is here, here is 15, here is VZ. Let's say we chose VZ as 7. So here's 7. Right?
Okay.
So, right? So the 7 here is 15 over R1 plus R2 multiplied by R2. Okay? So you pick one. You pick R2. Once you pick R2, now you could calculate R1. Or you pick R1 and you calculate R2. You're free to do whichever one you choose. Right? This is giving you the ratio of R1 to R2 in order to maintain that point at whatever the Zener diode is.
And R will just be the Vn minus these, in this case, 7 over the current that go into the Zener.
Correct. And typical, as I was telling Kemma, typical low power Zeners, if you're not given any information in the question,
5 milliamps,
5 to 20, you're free to choose values between 5 and 20. Right?
Yeah.
So you could pick where you want.
And what would be the voltage drop on TR1? Would you say it would be like 3 volts? Like when sizing it?
No, well, you could calculate it here. We did that, right? So if it's an 18-volt transistor, then V unregulated at no load is 25. What is 25.46 how much?
No load, yeah.
25.46. They're saying a 1 volt peak to peak. So therefore the minimum going to be 24.46. Right? So here's at full load, here's 24.46, and here is 15. Right?
25.46 is 15 by root 2?
Correct. No, 18 by root 2.
Okay.
18 by root 2.
18? Okay. No problem.
Right? All right.
And it's just the voltage drop over the current that it had to supply.
Right.
I just trying to
So the maximum power is 2 amps and the voltage drop is 24 minus 59 point something. And then multiplied by 2 amps. So it's about 18 point something, nearly 19 watts the transistor being asked to dissipate.
Wow.
Yeah.
Okay.
Yeah. Normally those the power supply transistors and so on that we use in the lab, generally once you heat sink them properly, could handle like 50 to 100 watts fairly comfortably.
So so I did micro P before I did this course, and I built a power supply with just the transistor in parallel with the circuit. And it's only now like I know how to do it properly.
Right.
And nobody didn't even build a power supply like this. And I think we had all the parts.
Yeah. Well, no, right? I mean,
yeah.
is fairly straightforward. Hopefully, well, depending on whatever you're going to do or whatever else, at least you know what a pillar. If it's, even if it's a 12-volt regulator to charge your car battery, right? Yeah, so at least you know how to do it. You can size it. The output will be about 14.5 volts. Normally, to charge a car battery, you need about 14.5 volts to charge a 12-volt battery, right? And to trickle charge it, normally you need about 2 amps. So like this, so 14.5 volts, so you need about 14.5 volts on the output. And on the input, well, you could get an 18-volt transformer that could give you at least 2 amps coming from it, and you make your supply. And you have something.
Yeah, that's sounding good.
You know?
That's sounding good on paper until I make a fire hazard.
No, well, you have to put, like we mentioned, this is where the protection circuit comes in. This is why you need fuses and you need overcurrent protection. So you'll put the current limiting on this. So something like that. You will put a 2 amp, you will put the sense resistor and the current limiter inside of here. So the current, if it goes over 2 amps, it just shuts itself down. It will start to shut itself down. And you put something like a 3 amp fuse or something, so that if all else fails and the current goes above 3 amps, then the fuse will blow and the thing will shut off. Yeah, so always put a fuse, no matter what electronic circuit you're designing, always put a fuse on the in the system. Right? So you limit in the event that worst case short circuits or anything, so that the fuse will blow. And that guaranteed to eliminate any fire hazard because of something overloaded or anything. So
yeah, that makes sense.
You put a fuse on the primary.
So the wires won't burn.
Yeah, exactly. Right, you put a fuse on the primary side of the that 18-volt transformer. You put a fuse there, and if you want, you put a fuse on the secondary side too as well. Right, and hard and fast. So you short circuit or you go over the 2 amps or 3 amps, and it will blow the fuse. It's not regulated. It's not overcurrent protection, but in fact it is one-way overcurrent protection. You blow the fuse, so you have to go and fix the fuse to get it to work again, kind of. But it wouldn't burn any wires or anything.
So for the second part, why would you say that this configuration is better?
Kamaraj, answer that. We just did that. Answer it. Where we go?
I think I forget.
Okay, the difference between the two of them, right? The difference between the two of them is just the fact that the lower one, you supply the diode straight from the regulated supply, so that the voltage, the diode doesn't have to contend with a fluctuating voltage. One is a smaller voltage that you're supplying the diode with, so that the resistor is smaller, the bias resistor is smaller. And then two, if you supply from the unregulated supply, the Zener diode, you're going to have a ripple in this case, what is a 1 volt peak to peak or a 2 volt peak to peak ripple that the Zener diode will be subjected to, right? Although it gives a constant voltage, but it's still you're asking the bias current going through the Zener diode will go up and down as you're trying to depending on the load on the circuit outside. All right. So it's a more stable design. It's less stress on the Zener, and you need a smaller resistor because the unregulated supply voltage is less than the unregulated. All right.
That would make sense because the V will be the 15 volts and the Zener will be the 7.
Yeah.
So 15 minus 7 on the current are going into that.
Yeah.
For the
right?
Zener.
If it's a 5 milliamps and so on, and that is it. Right?
So I guess it's just the overcurrent protection stuff I think I have to learn.
Yeah.
And that'd be it for power supplies.
And that is it, yeah.
Camera, do you understand the previous one, like how it does work fundamentally?
Not 100%.
Which one? The
If you
op-amp
pull it
one?
back,
The second reason, configuration, why this is better than the previous one.
okay, well, I could tell you, right? So the Zener diode won't have to contend with the input voltage, which would be 18 volts. Now it just contended with 15. It won't have the ripple from the input. You know, it's how it have a 1 volt peak to peak ripple from the input. And because it is 15 volts going into it instead of 18, the resistor will be smaller. So if your size in the resistor is 15 minus the Zener voltage over the Zener current, so instead of 18, it'll be 15. So you have a smaller resistor.
Not 18, 25. Remember the 18 is AC, yeah? That's the transformer
Right.
secondary. Right, so the unregulated voltage is going between 24 and 25 volts. So that resistor now, the difference between, let's say it was a 7 volts then, is 7 minus, so 24, let's say 24 minus 7. It will vary between 25 minus 7 and 24 minus 7. Right, whereas on the outside it's just a flat 15. Yeah.
Yeah, so instead of 25 volts, you're just working with 15.
Because of the Zener diode.
Because we're connected
Because
in that.
Because it after the transistor now. You know, before the transistor is 25, after the transistor it'll be 15.
Oh.
Yeah.
Yeah.
All right. Well, okay. So, but if again I'm still around,